o'clock or something?
It's up to you.
Should I have the 2 lectures now? Yes. But should we have a break then in the middle?
If you want, you can have it.
I think it's better to stretch a little for the students normally, at least. Okay. So very nice to come here to India and Allahabad. And I will talk a little about this integration of high penetration of solar and wind power in power systems. I will be very short now, starting with myself. I will come back to that in a later lecture. And I am born in 1956, so I just turned 61. And I have worked with wind power integration since 1982. I made my PhD in wind power integration in 1988. And I can generally say that at that time, wind power integration, I mean, the fellow colleagues asked me more or less, why do you want to spoil your life in that? That will never happen and never become anything. But it's completely changed nowadays. And so today, everyone is very interested in this with high penetration. And when the question is what I mean with high penetration, that is also an issue I will come back to. Because there have been a very big change in what is high penetration. In the beginning, if you can see papers from the 80s where high penetration was that you can never have more than 5%. I will show you a paper later where you have where I have summarized studies of in several countries where you study 40% of solar and wind power, and that is more or less not a big issue. I mean, the question is when you come up to what they are discussing in Germany, for example, which is 80% of solar and wind power, then you come up to new challenges of storage in hydrogen and so on. Okay, so but here I didn't know exactly what is your background. It's probably a bit different, and because of that I will not have a lot of equations here. Just about this, which is a bit, just to say something about, I will have a lot of examples from Scandinavia. Just about, for example, Sweden is not that small. I mean, if you see that Sweden is, the length of Sweden is 2,000 kilometers, which is the same as from Allahabad down to Coimbatore in Tamil Nadu. That is, I found on the map, that is 2,000 kilometers. I will come back with these 3,000 kilometers, why that is interesting. But Sweden, we are Sweden, and then we have Norway, and we have Finland, and then we have Denmark here. And we are one synchronous power system, and that is extremely important from the balancing point of view, which I come back to later, where we have 50 hertz, and it's a synchronized system with Finland, Sweden, and Norway, and eastern part of Denmark. And then in Sweden, we have a huge amount of HVDC here around Sweden. That is one of the backgrounds why ABB, former ASEA, is such a company, because we need a lot of HVDC in order to be connected to the other countries. So here are here's a back-to-back link. Here are 2 DC links. Here's 2 DC links here, 1 DC link here. Here's 1 DC link, DC, 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 and there will be new DCs from Norway to UK and from Denmark to UK and so on. And KTH is, of course, here in Stockholm. Second biggest town in Scandinavia, because Copenhagen is slightly bigger. Okay. So I will talk about generally about electricity and about the wind power, and I will tomorrow it will be more solar power, and so I will talk about voltage control. So it will be today and tomorrow it will be mainly voltage, because you have 2 fundamental challenges in the grid, and that is to keep voltage. You should have 220 volt here, as I understand it, not too big difference. 2 big changes, and then the other issue is that exactly when you push the button, you have exactly at that millisecond you must have generation that is compensating for that. And these are the 2 fundamental issues: keep the voltage, keep the balance. So I start with something I call electricity. This is something new I started with some a year ago, just to get a feeling of when we are talking about balancing, what are we discussing in reality. So this is extremely fundamental. This you know. This is a torch you put on a lamp, very simple. Just remember that exactly when you put it on here, now, exactly when you did it, you get the electricity here, and exactly at that millisecond it came from the battery. Because the speed here is the speed of light. Okay? Very simple. Next step. You do exactly the same thing from a hydropower station, which is in Sweden, 1,000 kilometers away from where you put your torch, you put your lamp on. Remember, this is all like this. This is not totally true. This is, I recorded this, and this takes around, the sound here takes around 1/100th of a second, or something like 10 millisecond or something. So this is slower than the speed of light from here to this. So remember, exactly when you push the button, at exactly that millisecond, some generator somewhere is feeding your power, is sending this, is putting on, is producing more. There's absolutely no storage in the electricity grid. Exactly when you get the electricity here, exactly at that millisecond, it comes from a generator somewhere. And this is the fundamental balancing issue. So there is a discussion that the system operator should keep the balance, which is completely wrong. The balance is already always kept. It's not that you should keep a high reliability, but it's absolutely physically impossible to consume here with having at exactly the millisecond the same production. It's physically impossible to produce something without at exactly the same millisecond have a consumption somewhere. Then you have losses in the system, yes, that's okay. But this is in reality always kept in the system. That's why I have this with 3,000 kilometers. When I talk to you, let's say you are sitting 3 meters from me, you think you hear what I say. That's not correct. You hear what I said 10 milliseconds ago. On at that time, the electricity can move from Delhi to South Kerala. That's extremely important to remember, that the balancing issue is a huge thing. It's not an issue that the balance if you push on the lamp or the bulb here in Allahabad, that it has to be compensated in Allahabad. Forget it. We are discussing a whole India issue here. Here, we have the same thing again. From here, if we are here in Allahabad, the electricity, it takes less than 1/100th of a second, 10 milliseconds, to move the electricity from here to here. So when we are pushing on a bulb here, this means that whole India, since as I understand in the normal state at least, whole India is a synchronous power system. This means that since you have the same frequencies on AC system here, what you do here is totally can be compensated. You can never say that a power plant here is in the millisecond base compensated here. It's compensated all over India. This is, of course, a big challenge to get this to work, and that is the fundamental issue. How do you get that to work when you have more wind and solar power? So that is that's why balancing is such a fundamental issue, because it has to work in some way. Just to say, because I will have more examples, the examples of Nordic system, but then it's just to see that the Nordic system is like this. So it's more to say that it's this. When I talk about the size of the system, I will talk about this kind of size of the system. In Sweden, just a very small issue. In Sweden, we have a market, and that means that sometimes it's very windy in Denmark here, and then we have a market states that, okay, how to compensate that the wind is going down in Denmark here, for example. Yes, and then we take the cheapest bids, and then it's perhaps compensated in hydropower in northern Finland. So the distance for that is that, okay, the wind is decreasing here, so then we compensate it here. Okay, and then of course you have to arrange this in some specific way, and that is the challenge, especially when you give huge amount of solar and wind power. You have to organize this, and then there must of course be room in the grid in order to make this possible. Okay, so we have this issue, and that is that exactly when you push the button, exactly at that millisecond, you will also get the power from somewhere. The question is from where? I mean, how do I know that it comes from this way? I mean, you can say it's the same thing that if I push the button here in Allahabad, where does the generator, which generator is compensating that? Because that, of course, has an issue, have to do with how your grids is loaded. If this is compensated south of Allahabad, then there must be let's say, some kind of room in the grid from the south. On the other hand, it's coming from the west, and it must be room in the grid from the west. So that is one really fundamental issue, how this is handled. This is the so-called primary control, but it starts with the inertia, which I will come back to later, which is a challenge when you get more solar and wind power in the system. Or Sweden. In reality, this is with the so-called droop control that you have in the system. But I mean, the important thing is to understand that this is a really large-scale system. We are never talking about keeping the balance in Kerala or in Allahabad or anything like that. It's a wide-scale system when you have a synchronous system, which is, of course, efficient, because then you can share this, because it may be that I'm putting on my bulb here and another one is taking, they are decreasing their life consumption in the large system, and then you don't have compensate anything. If the wind go up in one place and it go down in another place, you have no problem. For example, here, we take back. If the wind is increasing here at the same time it's decreasing here, then you don't have any problem. So then, that is very good to have a large interconnected system, and that is what I have heard and understood, that is what has happened more and more in India, where you have integrated larger areas, and that is, of course, very good to do that. And then when we have wind power, so then we can have wind power, for example, somewhere here we have wind power in southern Norway. I had this because I had a speech here in Norway about the same thing, so that's why I had this. So then, of course, it may be that when it's windy, you get the wind power here, and when it's not windy, you get the power from somewhere else. For example, in Sweden's case, you get it from hydropower here. And this is the fundamental. This has nothing to do with, I mean, formally I show wind power here, but this is total system balancing. This is nothing new. This has going on since 1920s, or when you started with these bigger systems. And then what is happening now is that they have found out that it's very rational to have much bigger systems than you have had earlier. So the way, and I think this is rather important to remember. Electricity is mainly a transport system. It's not the source. The source is, of course, a power plant. When you push the button, you get the electricity, but at exactly that millisecond, it's a power plant. For example, what is discussed, for example, is electric vehicles. Is that a good thing? Okay, where does the electricity come from? I was in a seminar in Sweden 2 years ago, and that was a person, we were discussing wind power, and there was a person from Volkswagen in the panel. And I asked him, but why are you here from Volkswagen? And they said that, yeah, you know that if the electricity to my electric car comes from brown coal, then from CO2 point of view, it's better to run our diesels. And that is a really fundamental issue, that you have to think about where does the electricity come from? Just to go to electricity, an automatic thing. It's okay because you can easily clean in large-scale units, and maybe your local, for example, if you have a diesel engine, for example, the efficiency is only 20% or something, while a power plant today can have an efficiency of 40, 50, 60%. But if you have large losses and you have a bad power plant, I don't see, it's not an automatic, it comes to a point of view if you move to electricity. It has to do with a lot of details. So electricity is a transport system, but it's an extremely efficient transport system. That's why we have it. And the benefit of these power grids makes it possible to use distant sources. And that means that sometimes it's windy in that area, sometimes it's windy in that area, maybe it's sunny there, but when it's not sunny, it's windy in somewhere else, and so on. And then you have the hydro that you can balance with, and you can make an efficient use of all your sources. You can combine them in a good way. So these are, let's say, the fundamentals. So it's important to understand this kind of really big scale, but that, of course, also makes it more complicated. For example, if someone asks me, if I push the button here in Allahabad, where does the electricity come from? That is an extremely long answer to start with that. Then you have to have the grid model, you have to see that you have the initial response from the inertia all over India, and then you have the primary controls, you have a distribution, and then depending on the impedances and so on, it moves around. So it's to answer that very small question. Where does electricity come from? Challenging. So, the power system. Why do we have a power system? As I said, that it's the same, of course. I mean, what is good with power systems is that wherever you learn it, you can use it somewhere else. Power systems are more or less exactly the same all over the world. You have the same basic fundamental issues and the same challenges. So that's very good to learn this kind of basic technology. So, for example, the aim of the power system, the basic thing is that exactly when you push the button, or whatever you are using for kind of electricity, you store your cell phone or your exactly when you push the button, now I want electricity. Exactly at that millisecond you should get the electricity. And this should work no matter if it's sunny, windy, outage in lines, whatever happens. You push the button, it should work. That's what you want. And this means, and exactly you have the opposite. You have a wind power plant. You are sending in power. You want someone to exactly that millisecond, someone has to consume it. Exactly that amount. There are some losses, of course, but that is so the fundamental issue of this is that there is always a balance between total production and total consumption. And that should be handled. It's not that the physical balance should be handled. That is automatically handled. It's physically impossible to consume without the production. So if you get your consumption when you push the button, someone is producing. Be sure about that. That is nothing that you have to, that's energy balance. The challenge is to get it in a good way. So you don't, when you push the button, you get a blackout. That's not so nice. So, and the other one, so that is the fundamental issue, which is the balance. This can be deregulated. The question is where you get the power from, when it starts and so on. Liberalized, or what you call it. The other one is that you want to have a realistic voltage. In Sweden we have 230 volts. Here it's classified as 220, I think. We had 220, and then someone said that now you don't have 220, now we have 230. So they raised the voltage a little. So, but nothing was changed. So it's just classified as 220. And then, of course, this should be, both these points should be with some kind of certain reliability, because sometimes you get outages. That happens everywhere. And then the question is, it's not economically that whatever happens, it should never be any problems. Then it's extremely expensive. Then they have to have so much redundancy, extra power plants, parallel lines, and so on. So this is never 100%. Never, ever, anywhere. The question is, what is a reasonable reliability? That is the question. And then, of course, it should be economic and sustainable, of course. And sustainability is an issue that is discussed more nowadays than earlier. And that is, of course, the challenge. This with economic. Then, of course, okay, you have a lot of power plants. Which should I use right now? Should I use that one, or should I use that one? So on. That's the question. And these are the fundamental challenges, some of the challenges. This is the CO2 emissions that have increased in the last years. So what you see here is 90s. It has increased with, it has doubled since 1985 here. So this is, of course, a challenge. These are the CO2 emissions, and the idea is that this should, or the goal, or the must, or how you see it, is that this should decrease in some way. This is the challenge. This I show for all countries, different places, that remember one thing, that if this should decrease, if we have the same amount of population in the world, if this should decrease with 50%, let's say that, then of course the mean value per capita must also decrease to 50%. And this is the mean emission per capita per year currently. India is significantly lower than that. So let's say you kept this level and everyone else in the world decreased to the same level as India, then then you can say that then we have decreased the amount of CO2 emissions to a reasonable level. The challenge is that this is not the way it looks everywhere. You have Germany, for example, they are much higher. Also Sweden, we have nearly 100%. We don't have we have nearly 100% CO-free electric production in Sweden, but we have a huge amount of cars and trucks, and they are consuming, and we have a steel industry that is consuming a lot of coal also. So that's why we are also, Sweden is higher than the mean. So also Sweden has to decrease to 50% or something like this. But then you have US, for example, and Russia, they have extremely much higher than the mean value. But that, I think it's extremely important to understand that this, for every country, this has to decrease significantly. But I cannot say that your power system is, from CO2 emission perfect point of view, but on the other hand, since you are so many, it becomes very little per capita. Which is, of course, very interesting when you start to see the challenges for the future, that we have to do something here. These are just some figures about what is happening with the climate and so on. I don't take these details here. What is happening nowadays is that solar and wind power has an extremely expansion nowadays. I think we have, I forget that figure, we have around 10 times more in the world solar and wind power today compared to 20 years ago. The challenge is, on the other hand, that it's increasing from a very small level. So we have a fantastic expansion currently. We have a huge amount of countries in the world now with, for example, Denmark gets 40% of their electricity, 50% from wind power only. So we have a very, but it's increasing from a very small level. So even if solar and wind, and it's becoming cheaper, and also you can see pictures from, I think, Saudi Arabia or Iran or country where they are pumping oil using solar PV to pump up the oil, because that is the cheapest way to pump up the oil. So even if you see this fantastic expansion, it's still from a very low level. So it's not that, I mean, this will within, let's say, just some years automatically change the challenge. But this is also very promising figures. These are costs for new solar and wind power. This is for solar power. And the solar power price has really gone down significantly. So what I've heard, some figures from a Swedish company called Fortum, who is investing in India, they say that new solar power now is in some areas cheaper than new coal power in India. But that is, of course, because it's so sunny here. But it's really coming down to very interesting prices. I will show you tomorrow. I have solar power on my roof, so I will talk a little about how that works in practice. That's in Sweden. It's not so sunny as it is here, for example. But solar power is really coming down in price. What is also coming down in price is onshore wind power is also going down in price. But the big change in the last 3 years, is that also offshore wind power, which you have a lot in Germany, for example, there we have wind power out in the sea. That has also significantly come down in price now compared to earlier. So all these kind of renewable sources are very interesting nowadays. This is a little about wind power. Wind power in itself is an extremely broad area. We have at KTH, we have had since many years, we have had a wind power course. The challenge of wind power is that you have, if you really want to be an expert in wind power, you have to learn a lot. First, you have the metrology. You have to understand how the wind is, where you have different winds on different heights and so on. And then you have, of course, that the wind is varying, and the gusts, I mean, how often is it a storm? So your wind power plant has to, and a hurricane, it may be a hurricane, and then of course you cannot accept that your wind power just fall down when it's a hurricane. So you have to dimension it for extreme weather and so on. So that is, let's say, step one. You have to know about this, have to feeling. Then you have aerodynamics, which is more the same knowledge as an aeroplane. I mean, you have the blades that can be twisted like this. The blades are twisted because you have different wind speeds depending on if you are close to the hub or if you are far out. And then you have, of course, what I will concentrate here, then you have the electric generation, but here you also have different technologies. You can have power electronics of different kinds. You can have control of active, reactive power and so on. You can have synthetic inertia, a lot of different things. Then you send out this wind power to the power system, and then at the end this also reach the consumers. And then, of course, the important thing, in some way, this one that built this one has to be funded. They must get an income. So in some way, money has to be moved from the consumers to the wind power owners. The question is how. And then the question is if the state is involved. As I understand from India, the consumers are not paying as much as the power plant are costing. So you get some kind of state subsidies in some way. In Sweden, it's the totally opposite. The consumer is paying a tax. We have an electricity tax, and then we have VAT on the tax. And then we have a lot of, if I look on my electricity bill, I think 1/3 is tax. So this is in Sweden a very big income from the state. Nice for the state. This is just some, I will show another graph later about this, but this is just say something. I mean, what I think these are the more, I often take up these countries as the interesting countries. You have, because from integration point of view, you have Ireland. This is Ireland. This is Ireland and it's an island at the same time. So they have one transmission line here, Wales in UK, and they have another line here up to Scotland. But in reality, they have to keep their balance themselves. And they have currently around 20% of their energy is coming from wind power. But in some specific situations, they can get 70% from wind power, from the power point of view, when it's very windy and it's not so much. The challenge for wind power is normally between the Saturday and the Sunday, when you have the lowest consumption. And if it's very windy in the night between Saturday and Sunday, you have probably challenges in the power system, because then you have a huge amount of wind power, but not so much demand. So this is on a yearly base, but on the capacity, I think they have up to 70%, I heard was the last figures. Portugal is also, then you have the Iberia Peninsula. They are also a very interesting area, because it's very isolated. They have one cable down here, an AC line, an AC cable down to Morocco, and then they have some connections up to France here, but they are rather small. These interconnections here are around, I think it's around 4,000 megawatt, 3 gigawatt, and that is very little compared to the total wind power. So in reality, they are keeping the balance themselves more or less in the peninsula. And they have 25% of the energy is only coming from wind power. Then they have solar power in addition to that on the yearly base. I know Portugal have had, I think, 4% more wind power production than their own consumption in several hours last year. That was the new data I heard. So it's very common to have, so Portugal is sometimes having more wind power production than demand in the country. But that is then, on the other hand, Portugal is much smaller than Spain, so it's compensated in Spain. Denmark has 45% of the yearly energy from wind, but that is not so strange, because when it's surplus, it's to Norway or Sweden, and then it's a very small country. And so they can send the surplus to Norway, a huge amount of interconnections. So they can send the surplus to Norway or to Sweden, and then when it's not so windy, they import hydropower and so on. Sweden, we have 10% of our yearly energy from wind power. So in Sweden, it's a very minor challenge, I can say. I think this is important to say, just to get a feeling when I talk about large and small challenges. Is this, for example, I'm working in an international group where we are discussing high penetration of wind power. And I can directly say that high penetration is a completely different thing now than it was 10 years ago. I mean, I don't think that they say, do you have a high penetration of wind power? Yeah. 25% of yearly energy, is that high percent? No, it's not so much. We can have up to 40. I saw a report from Germany where there was a guy that was very negative to wind power. He said that, no, you cannot have so much wind power. Yeah, up to 40%, that's okay. But I mean, 80%, that is difficult. So 40%, that was very small for a guy that was negative to wind power integration. So that a lot of these things are happening nowadays, that what is large amount or small amounts is very much changing nowadays compared to earlier. Then, of course, you have different systems, you have different challenges in different systems and so on. And you have much bigger challenges. I can say that these are current, they have the most problems today because it's such a small area. And that means that when it's windy here, it becomes windy. In Sweden, it's not the same. I mean, it's wind in the south, and then maybe not wind in the north. So it's a lot of minor changes, smaller changes. Okay, so this is, I will come into a bit more about this. This is the the wind power generation. First, you have, and this is a fundamentally important issue, how to understand this. Here, you have the turbine. It's moving around. And then you sometimes have a gearbox, because the generator, a wind turbine is moving around with this speed around. If you learn, what is interesting, we have a wind power course. If a wind turbine is moving like this, if you see a wind power on distance and it's moving like this, it's probably 6 megawatt. Because the tip speed is nearly always around 100 meters per second around. And this means that big turbines, they are moving slow like this. If you have a 3 megawatt turbine, probably something like this. Then you have this 250 kilowatt turbine moving like this. So if you just see it on distance, you can, just by seeing how fast it is moving, you can directly, if you are expert, you don't have to learn so much, you can look at, okay, there I see a 6 megawatt turbine. That's nice. Anyhow, and that means that on the other hand, that a generator, for the ones that can know machines, they have to be high speed. You cannot have a machine which is working like this. So you have to either have many poles in the machines. That's one way. That's also what you often have in hydropower, for example. Or you can have a gearbox, or you can allow this one to move. So this has to move rather fast, much faster than this in reality. So you have some many pole machines, and then you can see big generators with many poles. That is from an Enercon, for example. And then you sometimes also have a converter, which, because here you get one frequency, and then you want to have another frequency out to the grid. And you have this converter, and that has a very big value from the control point of view of the power system, of course, if you have this one. And then you have to control a lot of things, because remember one thing, if you have a certain amount of power here, this is the fundamental issue of, let's say, it's mechanical engineering a little. If you send in a certain power here, then you should send around, forget the losses, if you send in, let's say, 2 megawatt here, then you should send out 2 megawatt here. If you send in 2 megawatt here, and then you only send out 1.9 megawatt here, then this will speed up, because you are producing more than you are consuming in reality on the mechanical side here. So if you produce 2 megawatt of, you can call it mechanical power from the wind, and you send out less here, then this will speed up. So then when you have, and that is okay if you have a converter here. If you don't have a converter, if you have a direct connection between the generator and without this one, then you have a direct, then the speed of the generator is in reality set by the grid. That is extremely important to understand the fundamental of an electric machine. That an electric machine that is connected to a grid, then you have an extremely strong connection between the speed of the shaft, speed of the rotor, and the electric frequency. So in reality, a generator is in reality connected to the grid, but if you have a converter in between, then you can allow the generator to sometimes go fast and sometimes go a bit slower, which is good from the noise point of view and the aerodynamic efficiency point of view, for example. So now this is some slides I got from a PhD student. I will talk a little about tomorrow, I think, about what they are doing. But this is a PhD student. I can say a little about what this PhD student is doing. I will show it here. Here you have the transmission grid. Transmission grid, let's say 400 kilovolt or something like this. What you have today is the following, that you have a huge amount of power plants here, coal or nuclear or something. And they have synchronous machines, so they are keeping the voltage. So here voltage is equal to 1 per unit if you are an electrical engineer, keeping the voltage more or less. In the future, or when you have a huge amount of solar wind power, what is happening is instead that then you normally, the wind power stations are not connected here normally. They are normally connected to other grids in some way. You have impedances here, and then you perhaps have the wind power plants out here. In the future, what will happen is that you take away these ones sometimes, but how to keep the voltage? So then the question is, can you keep the voltage here by using the reactive sources here? And that technically you can do it. The question is how good it is. Because you have the converter here, and the converter here can produce active power, of course, depending on what you do here, but it can also produce reactive power if you have a converter. If you don't have it, you cannot. Then it's fixed. But if you have a converter here by different kinds, then you can do that. So that is the area there is, if you have this wind turbine and you take away the central, or you can more or less say it like this, that if you take away these ones, can you then use these ones? Technically you can. The question is, on the other hand, can you use this one and send out reactive power here? Then you will affect the voltage here. That is the fundamental issue. What you can do, of course, here is to put in static var compensation, power electronics, VSC, or capacitors, inductors, and so on. But that is, the question is that you don't need, if you can do it with these ones, which you already have there, then you don't need this one, perhaps. The standard today is that this one will only send out a P, that is only sending out cos phi equal to 1, so we normally only send out the active power from that one. That's the standard today. So here we have the wind is coming into the wind power station, and then these are pictures, and you often have different types of machines. Sometimes they're synchronous machines. So this is a machine. This is from he's teaching in our course about electric machine. This is just to show you the strong connection between that. This is the rotor, or this is the rotor of the machine in the wind power. So when this one is turning around, then of course you will get a certain frequency. In the synchronous machines, it's a direct connection between the speed of this one and exactly the frequency you get. So if you have a lower frequency, they will turn slower. If you have a high frequency, they will turn faster. Then there are different types of machines, and this is central for what you can do. You have 4 types. They are also called this, the type 4 generator, type 3 generator, depending on what you have know about wind power. You first have the basic thing that was so-called, you only had an induction generator that was directly connected to the grid. An induction generator means that it consumes reactive power, and you have no controllability of the reactive power at all in that machine. That is not so efficient, and the problem is that then you get a constant speed. That is a problem with the speed is the following, that what I said is the following, that you have, if you draw it like this, that you have a generator, and then we have the turbine, and then we have the grid. Assume that you have, let's say, 50 hertz here. What you want to do then is, of course, if you have only a generator and then this one will turn with a constant speed. It's slightly different if you have an induction generator, or if you have a synchronous generator, induction generator, then you have the slip, which is some 1%. But in reality, if you have a fixed frequency, then you have a fixed speed of that one. This means that when it's 4 meters per second, it will have the same speed as if it's 15 meters per second. And at 15 meters per second, you produce a huge amount of power, while at 4 meters per second, you nearly don't produce anything. From aerodynamic point of view, you want it to run slowly when it's not so windy, but you want it to move faster when it's more windy. So from economic energy efficiency point of view, you want this to have a variable speed. That is physically impossible to get when you have this kind of thing. You could have a gearbox with where you have more as in a car, where you have, okay, low speed, 1, a bit higher speed, number 2, and then, but then you need a gearbox where you are changing, and that is more complicated. So this was one of the drawbacks of this induction generator, squirrel cage generator, that it's not so good from aerodynamic point of view. Another issue is the noise problem. That the noise from wind power is, the problem with noise is that since it's the tip speed that is moving around, and the noise is higher when it's very high speed. And then, of course, you will get very high noise also at low energy production. So you want it to run slower when it's not so windy and faster when it's very windy. And then you need a variable speed. And that you don't get with the number 1. Then you have a variant of this number 1, and that is number 2, but that is not so variable at all either. But then you have got these ones, 2 ones, where you have in reality the converter, which I talked about earlier. And then you have the double-fed induction generator, where you have a power electronics, and then you have the synchronous or induction generator with full-scale converter on the stator side. This, on the other hand, this is in reality the dominating technology today. But these are cheaper. But this is the dominating technology. This is what is happening today. And the reason is that what is happening nowadays is that in the beginning of the wind power era, the question was, I want to make a cheap wind power station that can generate electricity. Today, wind power is an integration issue. I mean, as I said, in Portugal, sometimes they have more wind power generation than demand. Then you must manage the balance, you must manage the voltage, and how do you do that? Then you need more advanced technologies. So that is, so today, more or less, they are requiring this. But then also the cost of this has decreased significantly, because earlier this was you can call it a luxury type of wind turbine. But on the other hand, today, since that is the standard, then of course the price is going down also on these ones. So this is what I understand. They are more or less taking out the market, and that means that you have power electronics in the wind power plant that can produce active or reactive power, and they can have it controllability and so on. I will come back to the inertia issue and so on. So the type 1, I don't take these ones, these reactive power support. And then you have problems with turbulence and these kind of things. Type 2, I don't go through this one. But then we have this type 3. Needs in speed control are not more than plus minus 30% of rated synchronous speed. You have to have, there is a specific, you cannot have so much speed control in that one. Yes, sorry, you can have some, but not so much. This means that you can have, you don't need, as a starter, you don't need a need for a soft starter, which you also, because you have to, when you start it up, you have to first turn it on, and then you have to connect it to the grid, which is easier when you have power electronics. The problem of these generators, this fault right through, that has been discussed a lot. That, I mean, if you suddenly get a voltage drop, which is very short, then these ones can be disconnected from the grid if you don't have the right technology, so-called fault right through technology, which of course is a problem. And because you want to have technology to do this, you can also have rises to overall expenses of the concept, since this can happen, that you have a problem if you get a short circuit on the point of this one. So because of that, and that is the one that I will talk more about, is this. Now I see I forgot number 4 here. Okay. The benefit of the number 4 is that there you have power electronics, so you can control more or less everything out to the grid. But on the other hand, then you have one component more. You have the power electronics, you have to pay for the power electronics, you can have problems in the power electronics and so on. And it has to be controlled. I mean, it's not that you, if you have a system like this, the benefit of this one is that you have something that is rotating, you have a generator, you have a grid. It's an extremely simple technology. If it's windy, this one is turning, you get power. Very simple. On the other hand, if you have power electronics, you have to control it, otherwise you don't get out anything. So you have to make it work, but that is of course working. Okay, so that is the fundamental of wind power, that you have a reactive capability in the wind power plant. And then the question is, can you use that? That is what I will talk about now. This is more or less the same thing I talked about earlier. This is, you can call it a conventional power system. You have the demand here, the industries, you have the houses, the consumers, and so on. And then you have the power plants that are producing to the transmission system. And then what you do is, what is normally the way in these kind of systems is that here you keep the voltage, 400 kilovolt, you can transmit, and sometimes you get an outage in this one, and you compensate it in this one or this one. So and then you can easily decide, okay, now we run this one, and now we run this one, and so on, so you can match the demand with the production. And then you have transformers, and then you send out the power to the consumers. So so this is the standard way, you can call it, in a conventional power system. So the modern trends is the following, that you instead start to do like this. Okay, how does this work? This is sustainable, and then we have the hydro that is balancing, because the question is what is happening when it's not windy. Then of course you need to have power from other places. But the question is here how to keep the voltage. So you still have in some way to keep the voltage on this transmission system. And then the question is, can you do it using these wind power plants? That is the same as I wrote earlier. Technically you can do it, but on the other hand, you cannot do whatever you want with the reactive power in this one, because then you will affect the voltage in this point. The question is, how much can you do with this one? And that depends on a lot of factors, and I will go through what is the setup of this, and I will have some examples of that also. This is the problem, that you can get this challenges with the voltage if you don't control it in a good way. So the idea is here, how do you control the voltage in the transmission level when you have the production? It's the same with wind power, solar power, of course. If you have the solar power out in the distribution system, how do you keep the voltage in the transmission system, since that is one of the essential challenges? You can keep generators as synchronous condensers. I know that that is one solution in North Chicago. They had a nuclear power station earlier, but when they took away, when they dismantled the nuclear power station, they kept the generator. That is, of course, some challenges, because you have to disconnect it from the turbine, and then you have to make it work. But still, you can keep the generators. And then, of course, in reality, what is important with reactive power is that reactive power and voltage control, it doesn't need any active power. You can have a synchronous machine running in air, more or less, and then you are in reality, you can, with this generator, you can generate reactive power, so you can keep the voltage in the system. This is so-called synchronous condensers. They are purchased nowadays. I know in Denmark, for example, they have bought, I think, rather newly, 3 of these ones, and I talked to a person in ABB, and this is an increasing market of synchronous condensers in the world. And one idea is that that is, let's say, a good way of keeping the voltage in the system. You can also have SVC, which is static var compensation, which means that you have inductors, and you have inductors and capacitors, and then you can connect them to the grid, and you can have power electronics in between, which means that you can get a variable amount of active and variable amount of reactive power. And what we are, so these are, I mean, it's important to say that it's not needed that we do this. It's not necessary that we do this. But it's a possibility, and we should only do it if this is more economical than doing this thing, or keeping the generators here. So the question is not so much, is it technical possible? Yes, it is technical possible. The question is, how good is it? Is it a good version to do this, or is it not a good version compared to alternative solutions? But then, of course, to see if it's a good solution, you have to arrange, for example, look on the static behavior. You have to have control methods in order to do this, because there is, of course, a challenge here. That if you have, I mean, you have more grids here, and you have wind turbines like this. The question is that there is something called hunting, if you know about that, if you know with voltage control. Hunting means that this one is trying to keep the voltage up, okay? But a bit too much. So then this one see that, now this is too high voltage. I want to keep down the voltage. So this one is trying to keep down the voltage, and then of course if this one is decreasing the voltage, then this one is saying that, no, we must have a higher voltage. So that means that this one will try to keep up the voltage, and this one want to keep down the voltage. And then of course if you are not having good set values of that, then you can get, that is called hunting, that they are, let's say, working against each other, and then you can also get oscillations if you are making it very bad. So of course you have to design the controllers in a good way so this really works. You can have droop control, there are discussions around this. But this is of course, it's technically possible, and then you can have, I will look at that, load flow analysis, then it's very easy. Then you can say that, okay, this one produced 1 megavar, this one is consuming 1 megavar, and so on. And then you get a good voltage profile. But then if you want to implement it in reality, you have a control science. And the question is are they going to only look on the local voltage here? If you want to keep a good voltage there, should this one then look on the local voltage? But if you want to supply reactive power here, then you must have some kind of coordinated control of all these ones, so you are sending out reactive power here, or you are consuming reactive power if you want to keep the voltage here. And then you in some way have to coordinate these and perhaps also optimize the use of them in order to minimize the losses and so on, keep a nice voltage and so on. So this is the thing, you can call it the aim of his project, that is exactly to do this kind of thing, to see what we can do in this area. So the voltage profile controllability, and it's mainly the transmission voltage we are discussing, using full resources of equipment in the wind generator, and it has to do with reliability. The benefit is, of course, that if that doesn't work, then of course you can get something from these ones. I mean, here if you completely rely on an SVC, you have to have extra SVCs, since if you lose all the generators, you have to have margins here. I mean, the benefit is, of course, here you can use this. And let's say one alternative is also, let's say that you find out that this one is the best one, this is the cheapest one. But then you can say that, okay, if I have a problem in that one, then I can use this one as a backup. But okay, I can accept larger losses if it's only during some hours a year when you have an outage in this one. But you have to keep the voltage there, otherwise the system doesn't work in a good way. So that is the economic way, as I said, and that I think it's rather important to have this kind of economical view of a lot of these things. It's not necessary to use these voltage control, because some people say the following, that need in the future to have so-called ancillary services, so you need to have reactive support from this one. And then I say, no, you don't need it. You can do it in another way. But you should only do it if it's smart. And smart here, I mean, if it's economically, from the total point of view. And that means that you are not, let's say, causing a huge amount of extra losses here, but you don't have to invest in that one. Because you already have them. In these, I mean, when you have a full converter, you have already purchased these wind power plants, you have the converters there, why not use them? That's the idea also. Participation in distribution system in developing reactive power markets, that is discussed nowadays. Today you have markets for active power, but there is a discussion. I know that they have some ideas of that. They have it in Switzerland. I know they have some kind of reactive power markets where you are paid not only for the megawatt, you're also paid for the megavar. There is also a discussion in the question is how to do that. I can say that the general issue in Sweden currently is the following. If you have a transmission grid here, transmission, and then here you have 400 kilovolt, and then you have here a distribution system. These are different owners in Sweden. I don't know how it is in India. Are they different owners of these grids? Is it one owner? Okay, all the grid, okay. I mean, in very many countries, also in Europe, these are different owners. You have the system operator, they own this grid, and then we have another owner for this one. The question is here that, okay, you have houses here, you are consuming power. The question is, what kind of rules do you have here for the queue? In Sweden, the current rule is, and I know that they are moving towards that in Germany also, because they get a lot of challenges with the wind power and solar power here. They are saying that in the interface between the transmission and this is the so-called TSO, transmission system operator. This is the DSO, distribution system operator. Q should be equal to 0. How to do that? And why do that? It may be stupid, because perhaps you have to have a controllability issues here, you have to have the controllability issues here. On the other hand, if you say that I don't care, then of course the transmission system will get a lot of problems that may be caused by the distribution system. So there is a discussion now, how should we handle this? And what do I mean with Q is equal to 0? In Sweden, we say Q is equal to 0 is hourly mean values, plus minus 5 megavar, I think it is. That is the rule, and then the question is, but how to do that? Because what is happening in Sweden, I don't think you have that so far here. What I see in the town is that in Sweden, we have, in most towns, we have cables. Cables are producing reactive power. So the problem in Sweden is that you have a huge amount of cables here. They are producing a lot of reactive power sent up to the transmission grid. And then they have to take care of too much reactive power. That is the challenge we have in Sweden. And that is what is happening when you are cablifying. Here I see that's a lot of overhead lines in the cities. And that means that, of course, you are not consuming so much reactive power, but then you have the demand that is consuming power, but that is mainly active. So what we are doing here is first to look on the distribution grid's reactive capability. The question is here, how much can you send here? Q possible. You can consume reactive power, and that of course, because the question is from the system operator point of view. Let's say we go to this system. These generators are normally keeping the voltage here. Keeping the voltage means that you are supplying reactive power or you are consuming reactive power in these generators. And then you just have a voltage control in this one, very simple. The question is that if you take away these ones, you want the wind power owners to do the same. So you want to, from the transmission system operator point of view, they want to see this interface here. They want to see that, aha, if the voltage go down, then I want to have more reactive power. If the voltage go up, I want to send out reactive power. So they want a distribution grid with the wind power to work as a synchronous generator. That's what they want. But okay, you have, from reactive power point of view. And then the question is, how large is this reactive power controllability? Remember, these are things that will happen when you get huge amount of solar and wind power in your system. When we are talking about, that's why I have this here, it's the high penetration issue. Because when you take away the synchronous machine, you still have to keep the voltage in some way. That's what we are doing here. So there are a lot of things that you can do in this grid, of course. You can have capacitors, you can have inductors, where you have switches on these ones, and you connect them and you disconnect them and so on. What you also have is that these transformers are often controllable. This means that a controllable transformer looks something like this. You can decide on the secondary side if you should have a high voltage and you go up there, or you should have a low voltage. And so then this one is controllable in steps, normally of some percent. You can have a controllability in the steps on the secondary side. So of course, one idea, and that will of course affect the voltage in the distribution system, but that also have an effect on the reactive capability. Just to say it a little like this, that if you start to produce a lot of reactive power here, if you have a huge amount of wind power here, it's producing, then the voltage increases here, so you get high voltage here. But then you can decrease the voltage using the tap changes in this one. So then you have to, of course, to coordinate the wind power production, the reactive power production in these ones, and the setting in the online tap change. Okay, transformer. R and X ratios have found out in this project. It was natural when I saw the result, but this has a very big importance. RX ratios is the size of the resistance in relation to the reactance. And that I will show, I think, some slides on that. Yes. For example, in a cable, the reactance is very small. So there we have high resistances because the lines are much closer in the cable, so you get a very low reactance in a cable compared to overhead line where you have more larger areas, you get higher reactance. So this Rx quota depends, of course, on the resistance, which depends on the sizes of the lines, but also the X, and that depends on if it's a cable or if it's an overhead line. So that have been shown. I will show you in some. It's of course understandable. That has an impact what you're doing. Cables are better than overhead lines from that point of view. I will show you in a while. The question is also the distributed generation, the wind power. Where is it? Is it here in the beginning of the system, or is it in the end of the system? Here you have more sensitive voltage. Here you don't have so sensitive voltage. So the question is where you have the wind power or the solar power. And then, of course, where is the demand? Of course, if you have a high demand here and then you have a wind power at the same time placed as the demand, then, of course, you improve the voltage using the wind power. So all these kind of things have an impact. So this, we have made the studies. We have a paper on this in Manchester this summer. We had a paper, no, in Torino it was. I will show you this paper in a while. So we analyzed this specific system, and the question was how much. So here you have a distribution system, and then the question is how much reactive power can you send out or take up in the point where it 1 to 2 then. That is the problem, yes. And then, of course, you have point of common coupling, which is PCC there. And then the question is that in some cases, when you produce a lot in the wind power, then you are sending out power. On the other hand, when you are not producing so much in the wind power, then you are consuming power. But technically, you could still have the converters connected to the power system. So even if you don't producing anything, you can still supply reactive power, which of course could, for example, increase the voltage in the distribution system if you have problems with that. So you could, of course, otherwise you would normally consume reactive power in a high load situation. On the other hand, if you had the wind power, you could support that, and then you don't consume so much reactive power. But that also depends on if you have overhead lines or reactive power, and then if you have a controllable transformer and so on. So that is the point of power. So we get, in this case, it's an optimization problem. So the idea is to either maximize the Q that we are sending out or minimize it. So we are sending when you are supplying reactive power to the grid, or if we are consuming reactive power from the grid. And that is, let's say, by controlling the reactive power here and here and here and here. The question is how to maximize or minimize the reactive power there. And then, of course, a lot of local voltage requirements that you should, of course, the voltage should be within, let's say, plus minus 10% or something like that, out in these points, and in all points in the system, because you have points out there also where no wind power, so you must, of course, keep the voltage within realistic limits. So that is, and then, of course, you can have a lot of different situations. You can have a huge amount of wind power, little wind power, high load, low load, and so on, because they are not so correlated. And this was a paper that identificating of reactive power provision boundaries in a distribution grid. But this is with, you will get the same thing if you have solar power. The challenge is then that the solar power converters, one of the basic assumptions is here that we assume that the converters can be used also when it's not windy. And that is technically possible, but normally not a state. For example, in my house, I have a converter for power, I could technically produce reactive power or consume reactive power, but the setting is, of course, that in the night it's not connected, because then in the night, why converter is better to disconnect it so I don't create any losses. An issue here, if we go back here, an issue is here, should we consider losses or not? Because you get losses. When you are sending reactive power around in this grid, you will get losses. This means that you may increase the losses, you may decrease the losses, depending on where you are producing this reactive power, depending on the load situation and so on. So that is, of course, and depending on the power factor, what you have in the demand, what you are consuming. So this is, of course, a challenge, and then the question is, how much should we consider the losses? And then, of course, let's say that if I'm providing reactive power, it will cause me losses. In Sweden, it is like this, that we have a grid company like this, that we have a company that owns this grid. From the power system point of view, this grid owner is a consumer, because this grid consumes losses. So the grid owner here have to pay for the losses. And if they want to sell reactive power, is the transmission system operator say, I want you to provide reactive power, then the grid owner can say, okay, just pay me for the losses. We have to know that. And then the question is, of course, then the system operator may say that, oh, that's too expensive. Then I produce it myself instead. So then you come into reactive markets, because this is exactly the ideas that are going around now. How should we handle this in reality? Technically, you can optimize whatever you want. The question is what is efficient from total point of view. I'm talking too much, I think. 12:10. Should we just take 5-minute break, I think? To just stretch up. So I start again at 12:15.